Welcome to our Fireside chat on portable MR imaging. I'm Khan Siddiqui. I'm the Chief Medical Officer and Chief Strategy Officer in Hyperfine. I'm a radiologist by training, and I've practiced for a while and then moved to entrepreneurial side. I have had a bunch of different startups. I'm at Hyperfine. I'm responsible for strategy and how we take the company and scale the company across globally. So today, I'm very excited. I have one of my former mentors, colleagues, and friend, Dr. Eliot Siegel, will be joining us and having a discussion around portable MR imaging. We really got started with our founder, Dr. Jonathan Rothberg's vision to really make a difference in people's life, people who we love in their life, and create a social impact at the same time. And based on that vision, created a mission to democratize healthcare by making medical imaging accessible to everyone around the world. Or we really are here to make a difference in how healthcare is practiced. And as Jonathan says, create a fork in history on how things evolve. What is Hyperfine? So we are the world's first portable bedside MRI scanner. It's been about 5+ years of R&D effort to figure out how to get an MRI scanner to the patient's bedside. And that had led to reduce in weight of the scanner, the cost of the scanner, the power requirements due to improvements in miniaturization, as well as green electronics, use of deep learning to do image reconstructions that are much higher quality than would be possible at a low field strength. So the scanner is a 64 millitesla scanner that can be driven to the patient's bedside and image at the same time. And being a low field strand, that is very simple and safe to use. You can see the picture in the middle is Yale Emergency Medicine Department, where the person getting scanned with all the electronics around it has no issues. The physician in the white coat with the iPad in her hand is controlling the scanner through a wireless interface that talks to the scanner and able to quickly image. Because of going to a permanent magnet, the power and the advances we did in gradient development and other technologies, we've brought the power requirements down to less than for example, for a coffee maker. So it can really be plugged in anywhere you want to. And we had to miniaturize the scanner so it could fit in a standard door in a hospital environment. Being interested in pediatric MR myself, for me, the left picture here is just like amazing. This is the first time now a parent can really stand next to a toddler or an infant and image without requiring deep sedation or anesthesia for imaging, with no risk to the watch, the Fitbit she's wearing, or anything in her pocket that may be metallic. There's no risk for. When we thought of scanner being used in a point of care and clinical environment, we had to think about who's going to run the scanner and how do we need to make the interface such that anybody be able to run it and either scan it locally or even be able to scan it remotely. So you can imagine a portable tech or even a nurse in an ICU running the scan over there, or while staff is using the scanner, MR tech can be observing it remotely from the radiology department. So we really thought through how to make it simple. Just select the indication, hit play, and the scan starts. Because the scanner is wirelessly connected, the images can go straight to a person's phone, be a physician or a patient, as well as to local cloud-based packs that we provide, or local packs that a hospital would have. So once you think about the scanner that now does not require a Faraday cage, does not require all the projectile risk and safety related issues, the possibilities of where it can go are just enormous. Think of senior living facilities, nursing homes, sports athletic facilities for traumatic brain injury related applications, military frontline, as well as naval vessel applications, even in retail healthcare sometime in the future, and maybe even inside an ambulance as a mobile stroke unit. So there are a lot of future possibilities on where this technology can take us. It's my pleasure to introduce Dr. Eliot Siegel, Professor and Vice Chair of Radiology at University of Maryland, as well as Chief of Radiology and Nuclear Medicine at VA Maryland Healthcare System. Dr. Siegel is also Adjunct Professor of Bioengineering at University of Maryland College Park, as well as of Computer Science at University of Maryland Baltimore County.
Hi, Con. It's great to be here, and thanks for the invitation to the Fireside chat. I love the metaphor, and it's always been fun talking with you and getting together. And so chatting with you should be an absolute pleasure this evening, and it's a really cool topic.
As always, you are always on top of latest that is coming in technologies and always exploring new opportunities, and don't box yourself in a particular specialty. So how did your interest start in low field MR and portable MR imaging?
Yeah, well, I've always had a strong interest in MRI and actually had the opportunity to learn it while we were purchasing equipment many years ago. Had a chance to take some of the courses with the technologists. So I've always been interested in high field strength MR. But recently, I've had a really strong interest in the last many months and few years in ultra low field MRI scanning. That is MR scanning at field strengths lower than 0.2 Tesla. And so one of the areas that made me really interested, or one of the challenges, was the dean's office actually called me in one day, and the dean related that his wife had 2 or 3 friends that had recently experienced or posterior circulation infarctions, and that they were not recognized as having a posterior circulation stroke early enough. And so the dean kind of called me in and said, could you invent an MRI scanner that could fit into an ambulance? And when we initially had this conversation, it was probably, I'd say 4 or 5 years ago or so. And I essentially said, no, we don't have an MR scanner that I know of that fits into an ambulance. It would be wonderful to have something that we could have utilized in the ambulance or earlier on, and the potential to be able to have this ubiquitously was really exciting. And since then, I've been following the literature, and there has been a tremendous amount of literature that's been written on ultra low field strength. It just has not until now been translated into commercial systems. And as you know, I have a really strong interest in artificial intelligence applications and the potential to be able to have a system that uses deep learning that can essentially reconstruct images or acquire images 256 times, for example, faster, would allow the potential to have a scanner at 1/16. So let's say a sub 0.1 Tesla scanner that could have equivalent images to a higher field strength system. And all of these developments in research would suggest that there are many tremendous advantages now of technology in addition to AI that make 2020 really, I think, a year where it might be a turning point for low field strength MR. So I'm really excited about it.
And that's how most of these things start, right? For us, there's some personal story that takes us into that direction. I mean, same thing for me. My mom has been getting a lot of TIAs, and just seeing the agony of trying to get to an MR scanner to see what is a positive, negative, and how long it takes. That's what kind of motivates me in this direction too. How do you think, people should think about something like the scanner I have behind me, the 2 of them here? Like, to me, it sounds like the same paradigm shift, right? You're going from a completely new way to do imaging, and how do you think about the process engineering that goes with it?
Yeah, so to me, I think that we should avoid the trap or the pitfall of considering the technologies such as Hyperfine or, in general, ultra low field strength MR as just another type of MR scanner in just another lower field or less expensive or portable system, and completely rethink our workflow. And the potential to be able to scan a patient in the neuro ICU, for example, multiple times during the course of a day, the ability to be able to very rapidly scan a patient at a nursing home where there may be questions or issues without bringing that patient into the hospital, the potential to be able to have a unit that could be operated on or by an assistant, and then have it monitored remotely by a technologist that may be monitoring more than one system, are all ways I think we can completely rethink the way that we do imaging. Right now, the whole idea of taking a patient from the ICU or in the OR, bringing that patient down, I think decreases the ability to be able to do MR scanning. And sometimes by the time you can do it, the clinical question that you're trying to ask, where you want to intervene quickly, it's pretty much too late. And so the idea of thinking about this more like a lab instrument, thinking about it more as though answering a specific clinical question, rather than the idea that you've got a checklist of certain sequences and parameters, and you've got to essentially do the same scan that you would do in a high field strength MR scanner. I know that the scanner has the capability of being able to do that, but being able to do an abbreviated scan just to answer the question, has there been a significant change in my patient in the ICU since earlier this morning? And being able to even do a 3 or 4 minute scan, just enough to be able to answer that question. And so rethinking how we use the system to answer specific questions and maybe have these ultra short sequences that are tailored to a specific clinical problem, I think is a really exciting way that we can rethink and reinvent the MRI technology. And so, in orthopedics, for example, the potential to be able to do ultra low field strength MR rather than doing conventional X-rays is really exciting.
I mean, yeah, that's what we're trying to do also, is like, how do you rethink an application? It's not just a scanner, but it's a workflow tool, right? So as we think about our applications we are developing or partnering with other partners and opening up the ecosystem for other third parties to build applications on our platform, we are very much interested in thinking about it. How are we solving clinical problems? How are we actually impacting outcomes and not just creating images for somebody to go interpret?
Yes, and even the potential to create an answer to a clinical question without any images at all. I mean, the potential to do a really super fast scan in a patient that's not able to fully cooperate, or that you'd have to take off a ventilator for a really short period of time, and to even have a deep learning algorithm be able to make a determination of the probability that a certain condition that you're thinking about clinically exists or not. You could essentially use the system to acquire signals. So the whole gamut from emulating traditional high-end, high field strength scanners to being able to invent something that would literally just answer a specific clinical question with or without images, I think is really cool.
Yeah. So I think 2020 is a very interesting year, right? I mean, as the pandemic started, we really got a lot of interest from folks on a scanner dedicated for a COVID unit. And then since the FDA clearance we've received for the device now, it's been even more interest. So, but, just thinking about like, how has the pandemic changed radiology, and how do you think, is it temporary stuff? Like, is it going to permanently change how radiology is practiced?
Yeah, I think that these changes with the pandemic are going to be enduring and long lasting rather than fading away, as hopefully the virus will within the next several months. But the biggest changes that we're seeing are one, much more of a switch to portable imaging. The idea has been trying to do imaging at the point of care, the potential to be able to actually shoot through a window where a technologist is able to do a portable without being in the same room as a patient who's COVID positive. The potential to be able to have a single technologist monitor multiple other maybe non-subspecialty technologists in MRI or CT and be able to image remotely is something that I think we're seeing more and more of during the pandemic, and will be something that is enduring.
Those are very great insights.
How future-proof are these systems? Should I think of them as systems today for head scanning and extremity scanning, and in the future to be modified, or are there ways to be able to do in the field upgrades that will allow me to take advantage of the latest technology?
Yeah, absolutely. So, I mean, our first FDA clearance was for neuroimaging, but we're working on all other body parts also. So we've designed the scanner to be pretty much field upgradable, as you would think of it. I mean, from my previous startup, Higgy had the same kind of idea where we were doing field upgrades to devices. I think the limitation of upgrade will really be the magnet itself, right? So if you're not replacing the magnet, which has 100-year or more half-life, for example, rest are easy. I mean, the coils would be just plug in right there. You see the little black socket there. All the electronics in the bottom are all modular. So if you need to upgrade to a next generation of GPUs for better reconstructions or things like that, or improve some of the electronics back there, those are all modular, designed to be easily serviceable, easily upgradable and changeable. So I think the change really will become once you increase the bore size, right? So for example, this is a 30 centimeter bore, so any body part that we can image for pediatric or adult in that space, we will continue to evolve and build new coils and new type of imaging around that stuff. And then in the future, probably we'll have different kind of size of scanners that are dedicated for OR use, for example, or inside an ambulance. We'll have to think about what do we do where we don't need a motor and wheels to drive the scanner anymore. It has to be stationary. So those kind of changes will be there for specific applications. But I think our whole idea was to have a field upgradable system.
That's great. One of the things I love about my Tesla is the fact that it continues to upgrade itself with software. And those upgrades haven't just been cosmetic, but the upgrades have allowed increased range of driving. They've allowed better braking, safety improvements, and also, of course, the self-driving as well. And so would you see this scanner also being able to take wireless upgrades as time goes on? Would you see that something as being built into the system, or are there FDA regulatory issues that my car doesn't have to worry about that you guys have to worry about?
No, this is exactly how we're thinking about this. Actually, our current customers who've had the scanner in the research facilities as well as clinically, they constantly get these updates frequently, and it all depends on what the upgrade is about, right? Sometimes, and as part of our release cycle, our quality management system that we have to maintain all the stuff, we make the determination does it need to require resubmission for FDA. So, for example, the deep learning based reconstruction that we're bringing on in the future will require a new FDA submission, but a lot of the other minor changes may be just letter to file and not really require a lot of those updates. So, and that's exactly what is happening, right? I mean, we are improving gradient strengths by using software only. We're improving a lot of different other things in the scanner. Image quality has gone up 100% since I joined about a year ago for this. So, in this constant improvement that is happening in similar to what you mentioned in Tesla, right? Power requirements and gradient fields and image quality and different type of reconstructions and different clinical applications on top of it. So,
have these been tested in an environment where there may be changes in temperature, changes in pressure, outside noises and influences? Are there ways to be able to have the system adapt to its environment in an intelligent way as well?
So that's exactly how our scanner works, right? When you bring into the room and turn it on, the first 2 minutes does a calibration scan, where exactly looking at all the environmental changes and tuning the scanner to be able to perform consistent imaging across different environments, right? So, so that's exactly what we're seeing. Sometimes you're scanning in a room that has temperatures much higher, based on patient conditions. The next minute it's been driving down, outside maybe an image for some other reason, and that initial calibration that happens, and plus some of the sequences also have their own internal ways to assess and optimize for all those factors. I mean, you can just imagine, right? A nurse coming in the room with the iPhone in her pocket, walking around, and the RF noise that is generating by the phone could cause interferences, right? So, or they're moving the IV pole around for some reason, and we need to be able to continuously monitor this noise and environmental changes that are happening and cancel this out actively as we are doing the imaging. And our whole goal really is to, all you need to do is just put the patient inside the coil, and that's it. And then let us, the AI, figure out where the patient's head is positioned, how it's getting, how the planning is happening, and all that stuff is done really automatically. So there are a lot of cool technologies coming in the future where we are even doing things that are, doesn't even require any or correct any motion-related artifacts that may be happening also. Where do you see low field MR going in your own research and all that you've done?
So I think low field is going to catch on really in the next short number of years. One of the major vendors has taken their 1.5 Tesla scanner and actually for research purposes allowed scanning at 0.55 Tesla. And what they've demonstrated is that whether it's for imaging of the lungs, whether it's for interventional cardiac procedures and other procedures, there are not only the potential to be able to save money and have some better sighting considerations with a 0.55 Tesla system, but actually better images and safer images, being able to image patients that you couldn't do already. So I think, get ready for some competition from some of the major MR providers. The other thing is internationally, as you know, low field strength MR systems, whether it's in China or other areas of the world, are a much higher percentage of the MR systems that are being sold. And I think that that trend is going to continue. I think that the application of deep learning and AI is going to, in many ways, democratize the ultra low field strength, so that as many people start publishing and talking about some of the techniques, including your experience, I think you're going to find that you're also encouraging quite a few startups. There's so many innovative designs of magnet systems that are out there now, and so many different configurations, that I think we're going to start seeing really creative applications that use particular subsets of an application, maybe to look at scanning particular areas of the body and answering specific clinical questions. I think one area that's going to be really exciting is going to be combining ultra low field strength MR with radiation oncology. The ability to, in real time, track a lesion and be able to adjust the field and turn the dose on or off, depending on where you are with that, is really exciting. The potential to be able to do cardiac procedures where we have metallic devices that are of one type or another, catheters, et cetera, in the heart, and being able to image without those heating up. And so I think ultra low field as an adjunct to interventional procedures is going to get really hot in the short period of time also. And I think that the whole idea that Hyperfine is pioneering the way in, and sometimes it can be wonderful to be first in line, and sometimes it can be a challenge. I think you guys are really opening up an exciting new area of applications. We've had tons of research and tons of really good ideas and research systems, but actually opening the way and paving the way for ultra low field strength at lower than 0.1 Tesla for clinical applications and routine scanning is really exciting. But get ready for lots of competition.
That's exactly how we're hoping and wishing, and at the same time thinking about. I think it is a pleasure, as always, talking to you.
Yeah, the pleasure's mine, and congratulations. I'm hoping that trajectory of exponential advancements continues for quite a while.
Thank you.
Hello, I'm Brian Welch. I'm the Director of Clinical Science at Hyperfine. I'm coming to you from Guilford, Connecticut, Hyperfine headquarters. I'm here in our mock ICU, and today with the team members I have with me, we're going to demonstrate to you a portable MRI scanner driving into this room, docking up against this bed, and scanning this subject with a T2 weighted MRI. So, follow me.
All right, Brian is now in our hallway, and he is driving the device. It has a motor drivetrain underneath it. You'll notice his left hand on the right side of your screen on a joystick, and he comes in through the metal frame doorway. On his way in to docking at bedside, he's going to pause. He'll lower the bridge. We'll explain that in a moment. And he's going to show you what 64 millitesla looks like in practice. What kind of field strength is that? So with his metal keychain, you can see what that looks like here live. Importance being, for a portable device, not in a copper shielded room, is being able to minimize the impact or the potential for projectile events. So now he's going to continue his journey to the head of the bed. He's kind of watching his way in. He's done this a few times. Left hand on the joystick, aligning it, and just getting the gap right so that when he lowers the bridge, he controls for the space between the head coil and the head of the bed. Now he's going to take a standard power cord here, a 3-prong outlet. The system is very electrically efficient. It uses less than 900 watts of total power. So it's plugged in. And what he will do for purposes of our demonstration today is he will also connect it to wired Ethernet. It does work via hotspot, but just to ensure our connection today, he's plugging into wired Ethernet. All right, at this point, we are ready to load the patient. 1, 2, 3.
Once the patient is loaded, it's just a few more steps to get going with the user interface. So I'm going to share with you the user interface that you normally access via a tablet controller, an iPad controller. So the interface is a web interface. I'm logging in now. You start on the patient tab, and if you had a connection to a modality worklist server, you could automatically pull the details and order via that. But not right now, I'm just going to enter it in manually. And one feature that you may notice on the screen at the bottom is unique to us, is we have the ability to send an email to the team as soon as the exam is completed. So any emails that appear in this bottom text box will receive a message with montages of anonymized images, no PHI in those emails, as soon as the exam is finished. So I'm going to pop over here to the exam tab. We have a series of protocols that we can pick from. I'm going to pick the brain general. Other protocols exist for things like bleed, stroke, hydrocephalus, or headache. I'm going to take away everything except for this one T2 weighted exam. So I'm going to pick a T2 weighted exam that's a little bit better for this purpose. So I'm going to put that one in there, and I'm going to hit play. And it's very intuitive and simple. It's like picking songs for a playlist. And you can rearrange those. We can add pauses and other sequences as we desire. So the scan is started. You can see the progress bar at the top. You should be able to hear some buzzing sounds coming over the microphone. Notice that the subject has no ear protection. The sounds are very quiet, way below the threshold that requires ear protection. And as the data comes in, I'm going to switch over to the scan tab, and we'll see updates about every 10% of the scan. And from the very beginning, you'll see a shape of a brain and some of the anatomical features. I'll let you know that we are scanning a brain in a transaxial slice plane. And this is useful in the emergency setting in case you were to recognize something right away, a large mass effect or undiagnosed tumor or bleed. You wouldn't even have to complete the entire sequence in order to know what to do next, and you can pull the patient out right away. So there's our first update. You can already see axial slices of the brain. This is just going to get sharper and crisper and better as the scan goes on. Keep in mind this is only 10% of a about 6-minute scan that's come in so far. And we can see more details, the folds of the brain, the orbits. It's full brain coverage, 36 slices, 5 millimeters each slice, going down to the beginnings of the cervical spine. In plane, it's 1.5 by 1.5 millimeters. Just to go over a few more details of this system, which is a completely self-contained MRI scanner. There is no equipment room associated with this system. Everything that you see in front of you is the system. There are no cryogens, no liquid cryogens. It's a permanent magnet that's always on, a low field 64 millitesla permanent magnet. This room is not a special room. It is not shielded in any special way. You can take this into any hospital room or any other room in the hospital, and it can deal with any surrounding equipment that may be nearby. You can see a patient monitor is powered up behind, has no impact on the image quality, and the scanner has no impact on the monitor. So the sequence has completed, the sounds have stopped. There's going to be another 30 seconds of a final reconstruction. If there were another sequence that followed this, it would go directly into that next sequence without any delay, so you wouldn't waste any time. And when this bar goes green, that means that the exam is completed, the final reconstruction has been performed, and the name of the sequence will replace the text at the top that says building image quality. The final reconstruction has been completed. Just going to show you some of the ways you can look at the data. Here it is through in the axial plane. Scrolling through the slices. You can also, after looking at all the axial slices that were acquired, you can switch to one of the other orientations and reformat to the sagittal orientation. So this is a reformatting of an axial scan. Coverage all the way down through the cerebellum and the beginning of the spine. And finally, the coronal plane. We also have some tools for 3D visualization.